This is a story about the Earth. On Christmas Eve in 1968, the astronauts on the Apollo 8 mission took this picture from their lunar orbit, and it was our first observation of the Earth from space. Fast forwarding 40 years and zooming in 250,000 miles, satellites have given us much higher resolution pictures of the Earth. So this is a blue marble produced by NASA that has 1 pixel for every square kilometer for the surface of the Earth. The Earth's atmosphere is this shell that lives on top of the Earth. It's about 1/100th the radius of the Earth. And satellites give us roughly 1 million observations every hour of this atmosphere. So when we take those million observations and try and understand what the state of the Earth's atmosphere is at any given time, we need to use some sort of a computer grid. So what that means in practice is we lay down a grid on top of the surface of the Earth. Maybe there are 1 million locations at which we'd like to know things like temperature, pressure, humidity, wind speed in 3 directions, a few other things. And we'd like to also know those things at concentric spheres leaving the surface of the Earth, roughly 100 levels up into space. So you multiply those numbers together, you get 10 variables, 100 levels, and 1 million locations, and you have 1 billion variables you need to define to start a forecast in a weather model. So the science of blending the atmospheres that we get from the observations we get from satellites, where we have 1 for every 1,000 variables we need to define, that science is referred to as data assimilation. It's an active area of research in applied mathematics. So around the time that that picture was taken, there was a meteorologist by the name of Ed Lorenz at MIT who was trying to show the National Weather Service that their linear methods of forecasting the Earth's atmosphere were not going to be adequate. And so he devised this thought experiment. He said, well, what if we could feed perfect observations of these atmospheric quantities into an infinite computer with exact knowledge of the governing state of the atmosphere, the equations that Mother Nature integrates. And we would do this at a resolution of a cubic foot. So we're getting perfect observations at this scale. And he went on to show that even with that accurate estimate, we could only forecast the weather for about 2 weeks. The reason being that the stuff that happens inside these cubic feet cascades up the energy spectrum on that time scale after about 2 weeks to lead our prediction based on that estimate and the Earth's atmosphere to diverge exponentially in time. This became known as the butterfly effect, and this is an iconic image of chaos that resulted from Lorenz's work. So going back to observations that we can make of the Earth's atmosphere, one of the hard problems we deal with is clouds. So clouds are formed by these micrometer-sized particles of water aggregated together to produce structures that exist on the order of the size of this room. Clouds could also take up an entire continent in size. So the spatial scales are immense in this problem. In this sequence of images from satellites, you see there's cold air being brought down by the Gulf Stream over the Rocky Mountains and warm, moist air colliding with it coming off of the Gulf of Mexico. And that process produces very violent thunderstorms, and in this case, produced an outbreak of hundreds of tornadoes that ended up killing several people earlier this year in the southern United States. So, acknowledging that we don't have a perfect estimate for the state of the Earth's atmosphere, one of the things we do is produce a collection or an ensemble of best guesses for that atmospheric state. This is very important to hurricane prediction. Here you see Hurricane Irene from earlier this summer. And this cone of uncertainty that you see here is produced by taking various versions of Hurricane Irene, all within which our observational uncertainty helps us believe the hurricane to sit, and taking an average of all of the probability, all of the forecasts of those individual hurricanes to give us a sense for what the potential futures of Irene are. And in this particular case, the National Hurricane Center was able to predict 4 days in advance the path that Hurricane Irene would take. So moving beyond weather prediction, the National Center for Atmospheric Research has big computers. This is a global simulation of the Earth's atmosphere, and it runs on a computer that will do 10 to the 15 calculations every second. That's a petaflop. And at that scale, we're able to resolve things like typhoons you can see spinning up in the Western Pacific, and some of the large-scale features of the Earth's climate. We can also answer questions about the chemistry of the Earth's ocean. So this is a combination of observations from satellites of the sea surface temperature and salinity, combined with a model that understands the governing equations of the ocean, on which timescales are far slower. And what you're seeing here are concentrations of plankton advected around the ocean by the dynamics. And you can see the flickering you see is large-scale synoptic storms coming through clouds blocking the sun, shadows, so the plankton don't get sunlight. And at this point, I want to make this analogy that, in biology and chemistry, we have a laboratory. We can go and do experiments, right? We have just one Earth. That's something you see in that picture that the astronauts took. We have just one Earth. So this is our laboratory. And in it, we can ask questions like, well, what happens if the Earth's oceans get more acidic? Do some of these plankton populations no longer survive? And that effect obviously cascades down the food chain. So I've told you about a few models, a few versions of the Earth, of which we have one. What happens when we combine them all? So I'm going to conclude by talking about the Intergovernmental Panel on Climate Change, the IPCC. Every few years they put out a report describing the current state of the art in climate prediction. One of the experiments they talk about is how well the state-of-the-art climate models, roughly 20 of the best in the world, how well they reproduce the globally averaged observed temperature increase of 1 degree over the last century. So on this figure you see the observations of that globally averaged temperature anomaly. And you can see that during volcanic eruptions there's a dramatic cooling event of roughly 1/10 of a degree. But there's roughly a linear trend over this 100 years. And that the models do a fairly good job. It looks like kind of a mess. They call these spaghetti plots when they throw all the models together. But when you average them, you get this solid orange curve. And the models do an excellent job reproducing these cooling events, these fast time-scale events where volcanic eruptions produce sulfur in the atmosphere and block sunlight. The models also capture this observed trend upward by 1 degree. And in this modeling laboratory, the one that we have, the Computational Climate Laboratory, we can do experiments like turn off the Industrial Revolution. Tell the climate models that the concentration of carbon dioxide remained as it was 200 years ago. And we can ask the model what happens. And so here, all of the anthropogenic forcings have been turned off. The models still reproduce these cooling events due to volcanic eruptions. But the trend is gone. The 1 degree Celsius temperature increase, globally averaged, disappears. And the IPCC used this as evidence to conclude that it is very likely the case that humans are responsible for the observed temperature increase. And as these models are used to predict what the next 100 years are going to be like, what the Earth's climate will look like 100 years from now, I believe they're telling the most important big data story. The ability of these models to tell us what's going to happen, it's the biggest data story because if we get it wrong, if we don't pay attention to what the models are telling us, we could end up in big trouble. Thank you.